A2 Further Maths, Limits. Okay, so I've got an example of a power series here. So you can see you've got the coefficients at the front and the x increasing in powers. What I'd like you to do, please, is just see if you can find the derivatives of this power series. The first 4 derivatives will be fine, please. Okay, so pause there, see if you can find each of those. Okay, so let's see what you got then. So if you just differentiate the first one in terms of x, hopefully you would notice that a0 would have gone because it's just a constant, but the a1 next to x would definitely be put at the front, and you'd get this sort of pattern here. So you've got 2 lots of a squared, 3 lots of a2, sorry, 3 lots of a3, 4 lots of a4, and so on. Okay, so then you've got to go and differentiate again. So you differentiate it a second time. The a1 this time will cancel out. You're left with the 2a2 next to the x. And this time, this 3 here, but the 2 will come down. So you get this sort of pattern, 3 times 2. Okay, so we've got that. Again, if you do the third derivative, this bit cancels out. You're left with the 3 times the 2. But now you can see the same pattern, 4 times the 3 there. And the 2 came to the front when you differentiated it, and so on. And then I asked you to differentiate a 4th time. Okay, we stopped using the dashes there, put them before in. Sometimes they use Roman numerals in here, but it just means the 4th derivative. So if you do the 4th derivative, we can see this sort of pattern, and then I haven't asked for any more, and you can see, hopefully by now you're spotting what's actually happening every time you differentiate. Okay, so what I'd like you to do now is work out the values of each of those when x equals 0, including the original function as well. Just to have a go working out each of these functions when x equals 0. See if you can spot a bit of a pattern. Okay, so pause there, have a go at that. Okay, so let's see what you did then. So you put x equals 0 in. Well, for x equals 0 here, nearly all of the powers will disappear, leaving you f of 0 equals a0. This one, f dash of 0, is going to just get you a1, and then all these are going to be 0, so you're left with just a1. This one here, left with just that. This one here, the third derivative, when x equals 0, gets rid of all of these, so you're left with just that part. And then finally, the 4th derivative, if x equals 0, all of these disappear, and you're left with this. Now you can see a pattern coming here, 4 times 3 times 2, and you've hopefully noticed that this is exactly the same as 4 factorial. Okay, so what we want to do is we want to see, as it says there, what's the general derivative f of r. So it doesn't matter what value I put in here, what would that be when x equals 0? So not the whole of the pattern, just if I did f to the 5, f to the 6, f to the 7, could you work out for me what f to the general derivative r is going to be? So have a think about it, see if you can write that yourself. Okay, so I gave you a hint. I said to you, notice that 4 times 3 times 2 times 1, we can ignore the 1, all right, is going to equal 4 factorial. That's a nice hint to what the derivative is going to be. 4th derivative was 4 times 3 times 2. 3rd derivative was 3 times 2 times 1. 2nd derivative was 2 times 1. So therefore you'd expect for the general form for the any derivative is going to be r factorial times by a r. So no matter what number I put in there, I should be able to work this one out just here. Okay, right. So what I'd like to do now, rearrange each of these to work out what the coefficients a1, a2, a3, and so on are. Okay, now a1's already done, but can you go on and work out what a2, a3 up to the general form ar is going to be? So pause there, so think. Okay, so not too bad, hopefully. You notice that a2 could just divide by 2. So therefore it's find the derivative at 0, divide by 2 factorial. That would be your a2. So that gives you that value just there. How do you find a3? Well, you've got the third derivative. Sit 0 into it. Divide it by 3 times 2. 3 times 2 times 1, which is 3 factorial. Gets you a3. And so on. a4 is going to be the 4th derivative with 0 put in. Divided by 4 factorial, and this one will be a to the r. So that's a general form. Now what that allows me to do is to rewrite this function clearly A0 is just f of naught. A1 is just when the first derivative equals 0, so I can fill in those two bits. But I can rewrite this power series in terms of f of x or its derivatives, like that. So what's nice about this function here is you don't have all these unknown constants just here. You can work those out as long as you can find the derivatives of f of x. You should be able to work out what each of those coefficients are. Okay, so grab your notebooks then. We talked about Maclaurin series last year in year 1, but what you didn't do is you didn't actually know how the Maclaurin series produced the series that you used in year 1. And this is how it does it. It does it using the differentiation technique. So you can differentiate each of the functions and then substitute 0 into each of those derivatives. You didn't quite have enough calculus skills last year for us to introduce it at that stage, but now you're in the second year, you've got enough calculus skills, you could actually work out where these power series came from. Okay, so in your notebooks, just make sure you've got that down. You do get given that in your formula book. And what I'd like you to do is to see if you can actually make use of it. So I'd like you to use the power series to work out those, to use the Maclaurin series, sorry, to work out the power series for those three. Now you already know the answer because you've got the formula book in front of you, but just confirm where those formulas come from. Okay, so pause there, have a go at that yourself. Okay, so let's see. Sine x. So as long as you can find the values when x equals 0, as long as you can find the value, the derivative of it, and then substitute in 0 again, you should be able to write this power series. So the first one is sine 0, okay, because it's just the function itself. Then the second one is x times the derivative of sine x. Now, sine x, as you know, differentiates to cos x, so I can do that. And so therefore it's x cos 0. I differentiate cos, it goes to sine. Right, so back to sine, but of course it's minus. So the second derivative would go from sine to cos and then cos to minus sine, hence a minus. The x squared over 2 factorial is there all the time, but I can write sine 0 in. And then I keep going. So now it's going to be sine goes to cos, but I've got the minus stuck from the front, so therefore I get this, and plus dot dot dot. Okay, so keep going. So you can see what you're doing there. You're differentiating that function, the first function, and each time you're substituting 0. So if you need that extra hint for these two, do those yourselves, please. Let's neaten this up though. Sine 0 is clearly going to be 0. Cos 0 is going to be 1. So therefore that's going to disappear. I'm going to have x. That's going to disappear. I'm going to have minus x cubed over 3 factorial. And then that's going to disappear. So I'll get this sort of pattern. Okay, I'll put that extra one in there. So what do I end up with? Like that, which is where the formula book gets it. Right, what I'd like you to do, have a go at these two. So how did you do? So you got e to the x. What's quite nice about e to the x, of course, it differentiates to e to the x. So each of these derivatives are just going to be e to the 0. So I've got x e to the 0, x squared 2 factorial e to the 0, x cubed 3 factorial e to the 0, and so on. So simplify that out, because e to the 0 is going to be 1. You're just going to end up with this sort of pattern. In other words, you just end up with the coefficients on the front. What about ln? Interesting, ln 1 plus x. We'll talk about why it's not just ln x in a second. So we got ln of 1 plus x. First one is just going to be ln 1. Okay. The second one is going to be plus the derivative with 0 in there. So there we go. 1 over x is the derivative of, so it's going to be 1 over 1 plus x. But when x equals 0, you're going to get 1 over 1. And then you're going to get 1 over 1 plus x differentiated. So hopefully you can work that out yourself. And you're going to get minus 1 over 1 squared. And the pattern carries on. So we're going to get this part here is going to be 1 over 1 squared. So then we've got x cubed 2 over 1 cubed because the 2 comes to the top. Okay, it'd be minus 2, so that's why it becomes a minus and a plus. And then the 3 will come up next, that will be minus 6, because it'll be 2 and the 3, and so on. Okay, so that's where this has come from, and it just keeps going. Now what's quite interesting on this one then, you can see that 2 factorial and minus 1 on the top, they're just going to make it into a half. 3 factorial, so that's 3 times 2 times 1. Well, the 2 bit will cancel with that. The 4 factorial is 4 times 3 times 2, but the 3 times the 2 there and the 3 times the 2 here will cancel out, and so on. So this bit, this numerator here, cancels with some of that denominator there. In fact, it just leaves the first number. The bottom part is always 1, so that's just going to cancel. That's just going to stay as 1. So I end up with x squared, x cubed, x to the 4 over just a single number here. So we end up with that pattern, which is where the formula gets it from in the formula book. Okay, so well done if you manage to use Maclaurin series to figure out where those bits come from. Okay, right, pause if you need to. Just mentioned before, you can't find the Maclaurin series for ln x. It's not possible to do that because clearly at start you can't do ln 0, but just as importantly, when you do the differentiation of that, you can't find 1 over 1 plus x. Okay, because 1 over 1 plus x, you can find 1 over 1 plus x, but you can't find 1 over x, which is what this one would be, because if x equals 0, you'd have 1 divided by 0. So you can only find the Maclaurin series for ln of 1 plus x or variations of that. Right, so in your notebooks then please, grab that question down. You might want to have a quick go yourself. Okay, so see what you did then. Maybe you wanted to wait, it doesn't matter. So we're going to use Maclaurin series to find an expression for that up to x to the power 4. So first thing I'm going to do is find the Maclaurin series for sine to the minus 1 of x. I'm ignoring the x value entirely. I'll deal with that later on. So sine to the minus 1 of x. I know that if I've got sine to the minus 1 of x, I can differentiate that. Okay, you've just been doing things like this earlier on with differentiating inverse trig and inverse sine. So I know that sine to the minus 1 is exactly the same as 1 over the square root of 1 minus x squared. Okay, so I know that. Once I've got this part, I can differentiate that again. Okay, so now it's just plain chain rule, so I can differentiate the inside part, just going to get 2 minus 2x, but then the minus half comes to the front to cancel with that, so that's where you just get x, decrease the power by 1. Then I can carry on using the chain rule then. This time it's going to be product rule as well, because I've got an x, and so it starts to get quite messy. So I'm going to stop there. I'm not going to go much further than that. But this is where I've used the product rule, so differentiate that, leave that one alone. Differentiate this, and then we're going to get an extra 2 on the front, and so on. So just make sure you're happy and you can do that yourself. This is why I said to you it's important to make sure you can do product rule and chain rule efficiently. So I've managed to get the first 4. That's far enough because that's going to get me up to x to the power 4. I don't need to worry about doing any more. Although if I needed to, I could still do the chain rule, do the product rule, and get some more answers. What I do need though to use Maclaurin series is know what each of these are with 0 in for x. Okay, so if I do that, so I'm going to work out the Maclaurin series for sine to the minus 1. So I've gone there and I've just put in 0 in the first one, so I can see that. The second one I've got an x, so I'm using the Maclaurin series, so it's x times f dash of x with 0 in there. Then it's going to be x squared over 2 factorial, f dash dash, so it's the second derivative with 0 subbed in, and then the third derivative with 0 subbed in times by x cubed over 3 factorial. Okay, so I've got each of those. Oh, that's a bit interesting, isn't it? It's x to the power 3 when it wanted x to the power 4. So I don't know why I've stopped there. Maybe you've spotted it already. There's a good reason. Okay, so I've only gone up to x to the power 3. If you've gone up to x to the power 4 and done the extra one, not a problem. Not a problem. You've just gone a bit overkill. So I've gone down to that bit just there. Let me neaten this up a little bit. So once I've simplified it, it's going to just get me, that's going to cancel out. That bit's going to be nice and easy. It's just going to get used to 1. And so therefore, most of this will just end up cancelling. So an expression for, here we go. Not sine to the minus 1, but I wanted x times sine to the minus 1. So x times sine to the minus 1 is going to give me x squared plus x to the 4 over 3 factorial. So once I've spotted that, it saved me having to do the extra work. But if you've done the extra work, wouldn't have made any difference. And in fact, it would have gone to 0 anyway. Right, so what I'd like you to do, please, is have a go at completing the exercise on page 233, exercise 10A. Okay, so we're going to go back to investigating some limits. Now you have done investigating limits when you looked at rational functions. So a situation like the one below. We've got a rational function here. Can you use your rational function skills to find the limit as x tends towards infinity? As x gets really big, what will this function tend towards? So just pause there, do that yourself. Okay, so if you manage to say, yeah, I know the answer, it's 5/2, because I tried some big numbers on my calculator, and I can see that's what it's tending towards. That's fine. There's nothing wrong with that. I want you to see if you can remember how to solve it algebraically. So if you didn't solve it algebraically, all right, to prove that it's 5/2, you need to pause again and have another go at that. Okay, so let's see what you got then. So what do I mean by proving it algebraically? Well, if I tried to substitute infinity in now, what I'm going to get is infinity here and infinity here. And the whole thing will just go to infinity over infinity. But what I can do is I can do this sort of technique, dividing by the highest order power. So the top line could be rewritten like that, as long as you do the same to the bottom line as well, so to the denominator. And we can see that we get this equation. They're both equivalent to each other. There's no difference in there. This one's clearly more messy, but they are exactly the same functions. There's no difference. What is different about it is if I substituted infinity into this, or looked at how it tends towards infinity, I would have got infinity over infinity. But for this one, slightly different, because we know as x tends towards infinity, 1 over x and 1 over x squared tends towards 0, because it's 1 divided by a really big number, tends towards 0. So that means that this function just here, as this tends towards infinity, this bit and this bit are going to disappear, this bit and this bit are going to disappear, so we end up with just 5/2. So I've proved the result that I already knew by just putting in a big number. Okay, so let's look at a different function. This function here has got a trigonometric function as the numerator and a logarithmic function as the denominator. But I'm also looking at where x tends towards 0. Now, there is a bit of an issue. So what I'd like you to do is just try, first of all, seeing what happens to both of these functions as x tends towards 0. See if you can spot the problem. Okay, so you probably noticed that as x tends towards 0, sine x is actually equal to 0 at that point. So that's just going to be 0, which means that obviously at the moment this looks like it's tending towards 0. The other problem is though that the ln 1 plus 2x function, as x tends towards there, ln 1 is 0 as well. So the problem is you end up with 0 over 0. It's undefined at the point x equals 0. Okay, because this part just here equals 0. The problem is, if we actually look at the graph of the function, all right, we can see it's not because there's an asymptote. That's usually what happens when you're dividing by 0. The graph does seem to be defined just there, doesn't it? It's coming up. When x equals 0, it seems to have a value, right? But although it looks like it crosses, just that single point means it's undefined just there. Okay, it's defined all the way up to 0 and it's defined everything past 0. So if looking at a graph, it does seem to be a continuous line, but it's not. There is a problem just there when x equals 0, and we can see that because we can't divide by 0. So you need to be careful. You need to be careful when you see graphs because they look continuous and they're not, but also how to deal with this sort of situation, because it clearly means that these two values are tending towards a limit. And in fact, if you tried a very small value, you know, 0.01 or something like that, or 0.001, you could probably figure that value out just by trying some numbers. What we want to do though is we want to do it properly. Okay, so we want to find out when x tends towards that 0 through a limiting process like you just did, can we figure out what value that should be? Okay, right, grabbing your notebooks then. So we want to look at using Maclaurin series to solve or find the limit of the function. So what I'd like you to do, please, is I'd like you to have a go at working out the numerator as a power series and the denominator as a power series. So working out both the numerator and denominator. So pause there, do that yourself. Okay, so hopefully you got sine x to be that. You should have done straight from your formula book. The ln1 plus 2x though, you have to do a little bit of work because you're putting 2x in for where x is, but it's not too bad as long as you're careful. Don't forget you're doing 2x all squared, so that's going to be 4x squared. So you end up with this answer just here. So you've got your numerator and you've got your denominator. So what I can do is I can substitute both of those in. Notice I didn't give a limit. I don't care how far you go. We'll talk about that in a second. So I've got this value over this value. There we go. So these two are absolutely identical because this power series and this power series go forever. So they're absolutely identical to each other. So this function just here, written in this form, means I can actually work out the limit now because I'm back to the sorts of things I did last year with rational functions. I just need to use that same technique. Okay, so what I can do is I can divide everything by the highest order. In this case, it's x. So because this is x cubed and x to the 5. So I can divide everything by x to start with, makes it a little bit easier. And don't forget, I'm looking for x tending towards 0. So I'm looking at x tending towards 0. So as x tends towards 0, at the moment, if I didn't cancel out the x's, all that top line will go towards 0 and all that bottom line goes towards 0. But because x is constant, common throughout everything, I am allowed to divide by it. And also I'm allowed to divide by it because x can't equal 0 because I'm looking at the limit as x is approaching 0. So I've cancelled out an x. And now, in this situation, I can start to look at the limit. As x tends towards 0, these values here and every single one after it will go towards 0, leaving me the answer I want. So the limit as x tends towards 0 for that is going to equal just a half. And you could go back, and if you didn't do it early, you could do it again now or do it now. Just try in a value very close to 0 in there. You'll notice that the closer you get to 0, the closer this starts to approach a half. So you can use Maclaurin series to find limits of a function. Okay, stick with your notebooks. I want to prove that x cubed e to the minus x equals 0. Okay, so you might want to have a quick go yourself. I don't mind. If you want to have a go yourself, think about writing it as a quotient. Think about the function on the top and function on the bottom, and then you can pretty much prove it yourself. Okay, so pause if you want more time. If not, we'll have a look through. So the first thing I'm going to do is what I just said. I'm writing it as a quotient. So I've got x cubed on the top and e to the x on the bottom. So I've got that sort of situation. I can use Maclaurin series, not on the numerator, because that's pretty much done. That's already just x cubed. But the e to the x function on the bottom, I could definitely write like this. Okay. Just to double check, I'm looking for when x touches infinity. So I don't want all these powers here. In fact, I can divide through by this x cubed. That would make it a lot easier. So if I divide through by x cubed, then what I'm going to end up with is 1 on the top, and underneath 1 over x cubed, 1 over x squared, okay? Right, and I'm looking for when x approaches infinity. Now, as x approaches infinity, that numerator is not going to make any difference. These values here are all going to go to 0. I'm going to be left with 1/6 just there, okay? But that doesn't really matter because once you go past the 6th, you've got x over 24. Now, x is approaching infinity. These guys here are very small compared to infinity divided by 24. And that's even smaller than this, which is infinity squared divided by 120, and so on. So these values here are all going to go towards infinity. Definitely sort of gobble up those. So the whole of that value on that denominator is going to tend towards infinity. Okay. So we've got infinity as our denominator. Now, if that's tending towards infinity, look at the whole picture. We've got 1 divided by infinity. So the limit as x tends towards infinity is going to be 1 over this function that's tending towards infinity. What is it going to be? If it's 1 divided by a really big number, the limit is equal to 0. I've proved that result. Now what's important is you're able to understand and prove these results and make use of the general form of one. So pause if you're still one more time. Just make my last statement, therefore proved it. Okay. So this limit that we just looked at, we did it for x cubed, can be done for any general k value or any general power, and the results are always the same. It's always going to be equal to 0. But you need to have the ability to prove it, and you can prove it using Maclaurin series, using that technique we just looked at. So I've wrote it as a quotient, and I've used the power series to rewrite the bottom bit, e to the x. The next step that I did was dividing through by x to the k. It doesn't matter what power this is, somewhere along this power series, it will be in there. Okay, this could be sort of hundreds and hundreds of digits down. It doesn't matter. Whatever value k is, it will appear somewhere because this is an infinite power series. At the point where that appears, after that, you're going to have just single values of x. Because if I divide through by e to the k now, these will just be over those. These are definitely going to tend towards 0 as x tends towards infinity. The value in the middle is the stopping point. Last time it was 1 over 6, this time it's 1 over k factorial. But past that point, this is where it gets important, is going to be x and x squared, x cubed. These values are going to blow up to infinity when x approaches infinity. These don't matter because within that, if those are infinity, these are minuscule in comparison. In fact, these are all 0. So what's going to happen to this entire denominator? It's going to tend towards infinity. What happens to the entire thing then? 1 divided by infinity. So we can say that the limit as x tends towards infinity of this function just here, hence this function just here, is going to equal 0. So therefore the limit of any function that looks like that, so some sort of power there, x to whatever, e to the minus x, always goes towards 0. Now you can use that result. You might see this as a quick 1 marker. You can use that result if you've got it in a question, or the examiner may ask you to prove it, and to prove it you could use this technique here with the Maclaurin series. Okay, pause if you need more time. Okay, so let's have a look at another place where you might have the limit, solving an improper integral. So you've looked at improper integrals recently. So I've got this improper integral here between 1 and infinity. And I'll first of all ask, what would you need to do first if it's an improper integral? Okay, so pause there while you think about it. And if you want to actually have a go at it yourself, by all means do so, at least for the first bits. Okay, so if I asked you what you need to do with an improper integral, the first answer you would say to me is change that infinity sign to some value, some constant that we can tend towards infinity later. So I'm just going to replace the infinity for the value p. We cannot use infinity in our working, it would be wrong. Okay, so I've got this bit here. This is where I will stop and let you have a go. I want you to integrate that function then, please. So just start again once you've integrated it. Okay, so hopefully you integrated using by parts. If you didn't, pause again, have another go. So if you integrated by parts, then we'll notice that after the first bit, we would have got this function just here. Okay, so I'm differentiating that, leaving that alone, and so on. Differentiating that, integrating this one, which is where this bit comes from. And then because I've differentiated this just goes to 1, which is why it's disappeared here. So now I can work out this bit straight away because it's just going to get you minus the third on the front, on the back, and I can put those two bits together. I've then noticed that these two are both just e to the power minus 3x, so I can combine both of those, and simplify it to that. So very well done. But if you didn't get that, you really need to pause and have another go yourself and make sure you're happy with integration by parts. Right, once I've done that integration, I can substitute these two values in. So we end up with that value with the p subbed in there, and these values, which is just going to be a number that I can work out. Okay, because it's clearly defined at number 1. Okay, right. So what happens then? I'm going to get this to be 1 over 9 e to the minus 3. This part just here, though, I need to consider what's going to happen here. So at this point, I can start to consider what happens as p tends towards infinity. So as p tends towards infinity, let's just do both of these separately. This one just here is e to the minus 3p. So I could write that as 2/9 1 over e to the 3p. So I could write it like that, e to the 3p underneath. Now as p tends towards infinity, this value here is going to get very, very big. Now if this value gets very big, 1 over a really big number, of course, equals 0. So the limit of 1 over 3p, this bit, as x tends towards infinity, is going to go towards 0. This one just here, if you haven't spotted it, is what we were just working with. P e to the minus 3p is a type of function like this one we just looked at a minute ago. So this part just here, I can write down straight away is going to equal 0 because it uses that example. So the answer to this bit is going to tend towards 0, this bit is going to tend towards 0, so the answer at the end is just going to be 1 over 9 e to the minus 3 or 1 over 9 e to the 3. Okay, so pause, need to. Okay, we're going to look at a different theorem called L'Hopital's rule. So what I've got here is I've got two graphs. We're just going to do a bit of investigation work to start with. So I've got these two graphs. And I'm going to ask you to find the limit of not those two graphs themselves, but the quotient of f of x over g of x. I'm not asking you to do any algebra. I'm just having a look at what happens as they tend towards infinity. What do you notice about the function f of x, the red one, compared to the function g of x, which is the blue one? Once you get past the number 1, what's happening to those two functions? If you did one divided by the other, what's going to happen? Okay. Right, you might be tempted to think, oh, they tend towards 0 because they're both tending towards 0. But remember, you're not actually looking at what happens to each of them individually as they tend towards 0. You're looking at the value of this one divided by this one. Now notice that this value here, the blue one, is a lot smaller. All right, it's a lot smaller than the red one. So you've got a bigger number divided by a smaller number. That smaller number is tending towards 0 much faster than this one is. So really the limit of f of x over g of x, although they both tend towards infinity as x tends, they both tend towards 0 as x tends towards infinity, we can see that they're both tending towards 0. And you get this answer, okay, that f of x over g of x tends towards 0 over 0, which is clearly undefined. We can't do anything with 0 over 0. What we can see is because this graph here is bigger than this graph here, then what happens as x tends towards infinity is actually a big number divided by a very small number. So you're going to get, in this case, tended towards infinity. We can see that because it's a big number divided by a small number that's tending towards infinity. Okay, now when you actually consider it, the algebra, if you actually did the algebra for it, then we can see that f of x divided by g of x, just go back to the start, is x. And clearly that makes sense. As x tends towards infinity, this function x is going to tend towards infinity, so that's blatantly obvious. But it's interesting to make sure you can see it looking at the functions. Okay? Right, let's do the same investigation, but this time let's not consider the graphs of these. Let's look at the gradients of them. So consider the gradients. I'm not asking you to do any differentiation. Consider the gradients because you're considering the lines, the tangent lines. So for example, at number 2, there's the red gradient there and the blue gradient there. All right, so what can you say about the gradient of the red graph compared to the gradient of the blue graph at any given point? Okay, the gradient of the red graph compared to the gradient of the blue graph at any given point as it tends towards infinity. Okay, so again, same problem as before. We can clearly see the gradients are tending towards a flat line. They're tending towards zero, aren't they? All right, so we know that the gradients of these graphs are both tending towards zero as well. So they're both going towards zero. But what about the sizes of the gradients? So taking at number 2 as an example, notice that the red graph has a steeper gradient than the blue graph. And in fact, we always have the red graph having a bigger gradient than the blue graph. So the f of x function is always bigger than the g of x, and the g of x is tending towards zero at a faster rate than this one. Okay, so because that's tending towards zero at a faster rate, what's going to happen is you're going to have some number divided by zero. Anything divided by zero is approaching infinity. So although both f dash of x and g dash of x are zero, if you consider at what rate they're approaching it, the g of x function is approaching zero at a faster rate. So therefore you're dividing by zero, therefore the thing approaches infinity. Okay? And what that actually comes down to is this fact just here. As f of x approaches zero and g of x approaches zero, then we've noticed that the limit of this thing just here was exactly the same as the limit there. They were both, in this case, infinity. Although that bit's not important. What is important is noticing this fact just here. That the limit of this function, because it was 0 over 0, was exactly the same answer as this one. All right, those two were absolutely identical. You could do the same sort of event. Okay, so we've looked at what happens as they approach infinity. So what I'd like you to do is just spend a bit of time and investigate what happens to these two functions as they tend towards zero. Now we can see that as they tend towards zero, both of them are going to approach infinity. We know that. But what you're looking at is how they approach infinity. Which one is a dominant one as they approach infinity? And then what you can consider is what happens to the f of x over g of x function. So although they approach infinity over infinity as x tends towards zero, what actually happens when you compare both of those? Remember that different infinities can be different sizes. Okay, so pause there, have a think about it, and think about the gradient of those graphs as well. Okay, so what you probably noticed, or what you should have noticed, is that the g of x function is always bigger than the f of x function. So take any value, there you go, half is a nice easy example. This one came out as a 2, this one came up here as a 4. So therefore it's going to be bigger. All right. So we notice that this function here, the g of x function, is always going to be greater than the f of x function. So because this number here is approaching infinity quicker, you're doing something divided by a big number, then what's going to happen is that you end up approaching 0 because your denominator is bigger than your numerator. Once we've got that part, we can investigate what happens to the gradients. Okay, so what happens to the gradients? Now in this case, we're looking at the magnitude because clearly they're going downwards. So we don't want to look at the magnitude of them. That doesn't really make much difference. And we notice that the magnitude of the blue graph is always steeper than the red graph. Okay, take it there at the 2. You can see that there's not much in it, but clearly the blue one is a bigger gradient than the red one. Okay, so they share that in common, that if the function is smaller than that one there, then it's the same on the gradients. It's not always the case, so you need to be careful. So once I've got this part just here, I can then say that the limit, because this g function is greater, this is approaching infinity quicker, then you're going to have a big number divided by an even bigger number, and this is going to override this one, so therefore it's going to approach 0. Okay, as x approaches 0, this whole thing is going to start to approach 0. Okay. So same rule as before. What was important to notice is if your f of x function over your g of x function was infinity over infinity, then what we can say is because that limit was infinity over infinity, we know that the limit of its gradient function over its gradient function was going to be identical to it. You can forget the equals naught, it's that bit there which is key. Okay, right, so what is the point? That is L'Hopital's rule, but what is the point of it? Right, grab your notebooks then please. And what we're going to look at is just writing down what we just investigated then. So an alternative to Maclaurin series, it's a different option, is being able to use L'Hopital's rule. Now L'Hopital's rule states this: given any functions f of x and g of x, if those functions as x tends towards some limit, okay, it doesn't matter what that limit is, equals 0, so both of them equal 0, or if as they approach some limit they tend towards infinity, okay, both tend towards positive infinity or both tend towards negative infinity. So if that is a situation, not a mixture, can't have a mixture, you can't have that one tend towards 0 and that tend towards infinity, it has to be the same, both of those tend towards 0 or they both tend towards infinity, then this statement is true, that the limit of that function equals the limit of this one. Now why is that important? Well, you might be able to struggle to find the limit of this function just here. But just because you can't find the limit of that function, you might be able to find the limit of this function. This one might be easier to work out. And if you could find the limit of this function just here, then that means that you've got the limit of the original. So all you have to do is if you can differentiate it, and this gives you something easy to work with, therefore you've got the original. Okay, that's what L'Hopital's rule says. So make sure you pause and get down what you need in your notebook. Okay, to cover the rules about L'Hopital's rule, is it can only be applied if you can differentiate. So if you can't differentiate, if it doesn't exist, then you can't work with it. And the other rule you need is L'Hopital's rule can only be applied if they're both the same. So like I just said a minute ago, you can do 0 and 0, that's fine. Infinity, infinity, that's fine. But you can't have a 0 and an infinity or an infinity and a 0. They can't mix them. It has to be identical. And you need to be careful. Sometimes you get tricked out. I'll show you an example of that. All right, if you look at this rule just here, if L'Hopital's rule works, it can work more than once. So for example, if that equals 0 for 0 and you could differentiate it, great. And then because it works once, you could do it again. Now that might be helpful if you can find the limit of the second derivative over the second derivative. Maybe that's really easy to work out the limit. Then that tells you the answer to that one and it tells you the answer to the original. But the problem you might have is that, and this is where you might get tricked out by an examiner, that might differentiate to, that might be 0 over 0. Fine, we can use L'Hopital's rule. This one goes to something like 0 over infinity. But then this one goes back to 0 over 0. So you're sort of forgetting the middle step and realizing you can't actually use L'Hopital's rule because the middle step messed you up. So be very careful. Always just double check. What's the limit of that function? What's the limit of that function? Are they the same? Are they both 0? Are they both infinity? Yes, tick, I'm allowed to use L'Hopital's rule. Okay, so before I do L'Hopital's rule, I'll show you back to Maclaurin's. So I've got x over sine x. So I'm going to look at this function just here. So x over sine x used in Maclaurin series. Right, so just to fast forward slightly, we know that x over sine x equals that. Okay, and I can divide through by x then. So I get 1 over 1 minus x squared over 3 factorial. Once I've done that, I'm left with 1 over 1 as x tends towards 0 because this is just going to go to 0. And this is going towards 0, so I'm left with 1 over 1, so therefore the answer is going to be just 1. Okay, right, so what happens if I didn't use Maclaurin's and I wanted to use L'Hopital's rule? Okay, just grab your notebooks, because it's the first time we've done L'Hopital's rule. So I want to look at the limit of x sine to minus 1x using L'Hopital's rule. So I do want to think about the two functions. One of them is going to be x, one of them is going to be sine x. I need to check whether I'm able to use it. What's the limit of x as x approaches 0? Well, clearly that's going to be 0. What's the limit of sine x as x tends towards 0? 0. So therefore I'm allowed to use L'Hopital's rule because both of these are 0. Okay? Right, so then what I could do is I could differentiate both of them because I can't work that out on its own because both of them go towards 0. I'm stuck. But I can use L'Hopital's rule. L'Hopital's rule says if I can't work that one out and they both go to 0, I can differentiate both the numerator and denominator. All right, I'm allowed to do that and investigate what this limit goes to. So this example here, this limit for this is exactly the same as the limit for the numerator and denominator differentiated. Now this one I can do, can't I? So the numerator goes towards 1, the denominator goes towards 1, so therefore I get 1 over 1, which equals 1. So because that limit equaled 1, the original limit equaled 1. And that's why L'Hopital's rule is quite powerful. Okay, and that's an example of how to use L'Hopital's rule. Okay, so this just goes back to an example I said a minute ago of where you need to be careful about using L'Hopital's rule a third time. Notice this middle section here. Okay, if this was x cubed, for example, then you'd have x cubed over sine x. This will go to 3x squared over cos x, and you might go, oh, I'm going to use L'Hopital's rule again, and then flick it back to sine x. But the reason why you can't use L'Hopital's rule at this middle section is if this was x cubed or x squared, as x tends towards 0, that's turned towards 0, but the denominator would tend towards 1 because cos 0 is 1. So you do need to be very careful when you're allowed to use L'Hopital's rule. Always check, is it 0 over 0, is it infinity over infinity? Okay. Okay, so we're going to prove another important result. The other important result that's at the top of the board. Okay, which the examiner expects you to know. How can you use L'Hopital's rule to prove that this function is equal to 0? So just get it down in your notebook, then we'll investigate how to do it. Okay, so we're going to use L'Hopital's rule. But L'Hopital's rule says that you need to have a quotient. So how could I write this as a quotient? Well, the easiest way to write this as a quotient is by rewriting x to the power k as x to the minus k. If I have x to the minus k, then I could rewrite this function like this. Okay, and now I can clearly see that I've got a function on the numerator and a function to the denominator, and I'm okay to use L'Hopital's rule. Now I can either, because I can't work out both of these straight away, that's why I couldn't work out this to be 0, I need to just double check that they both tend towards the same value as x tends towards 0. So that's my first check. Now I've noticed that ln x, as x tends towards 0, this will tend towards infinity. I've also noticed that as x tends towards 0, x to the minus k, which is of course 1 over x, tends towards infinity as well. They both tend towards infinity, so I'm allowed to use L'Hopital's rule. I don't know what the limit this is, but if I can differentiate the numerator and differentiate the denominator, I should then, hopefully, be able to work out the limit of the original. So I'm going to use L'Hopital's rule. If I can find the limit of the differentiation of the differentiation, if I find the limit of that, it should be the same answer to this. So hopefully it's going to be 0. We shall see. Okay, but the first thing is, can I actually find the differentiation? Because if I can't, then I'm not allowed to use L'Hopital's rule. So can I find the differentiation of ln x? Well, the differentiation of ln x is 1 over x, or x to the minus 1. That's fine. What about x to the minus k? That's just a polynomial. I can bring the minus k to the front, x to the minus k minus 1. There we go. So I could definitely differentiate in both. So I'm going to look at the limit of the original function of the original function is equal to the limit of the differentiation over differentiation. Because both of those tend towards infinity, this has got to be true according to L'Hopital's rule. Right, Now, before I do any more work on this, let me just neaten this up. Have you noticed that x to the minus k, x to the minus half can be separated out? Or you might have just taken that underneath and cancelled them out. It doesn't matter. I've noticed though that that will cancel with that. I've also, just for neatness, x to the minus k I'm going to put back on the top. Okay, I can put that back on the top and make that a bit easier as well. So really, I've got this function just like this. Okay, right, what happens to this as x tends towards 0? So I've noticed that as x tends towards 0, this bit here, 0 to the k, is just going towards 0. 0 divided by any number, because of course k is any number you like, greater than 0. I've noticed that 0 divided by any number is always going to be 0. So I've proved this result just here using L'Hopital's rule. Okay, pause there, get whatever notes you need down. Okay, so what I'd like you to do is just have a look at exercise 10b on page 239. And there's some questions on there that all involve limits using Maclaurin series and L'Hopital's rule.